discuss about parallel resonance circuit. So consider a parallel resonance circuits where R, L, C are connected in parallel, and here current I is given here, current source. A general parallel resonance circuit consisting of ideal elements or resistance, inductance, and capacitance. These are ideal elements. In ideal elements, the inductor will not have internal resistance. Similarly, capacitor will not have any internal resistance. So these are the ideal elements: resistors, inductors, and capacitance, and it's connected across current source I. The conductance of R, okay, this is the resistance. Reciprocal of resistance is actually conductance is given by 1 by R, and susceptance, okay, reciprocal of this reactance is susceptance is given by YL is equal to 1 over reactance of inductance, that is J omega L. Okay, so it is given by, if you bring this J to numerator, multiply here J and here also J, then J square is minus 1. So that is where it's coming. This J will come here. In the denominator, J square will be there. J square will be minus 1. So we are going to get minus J by omega L. Similarly, the third branch, okay, that is the susceptance of the capacitor reactance. The susceptance of this one is given by 1 by J minus J XC. For capacitance, we are using minus J XC. So if you take 1 by J XC, and if you multiply once again here also by J and J, okay, so J will come here, and again in the denominator J square. J square is minus 1. So minus 1 into this minus becomes plus. So XC is nothing but 1 over omega C. X is nothing but 1 over omega C, and this omega C will come to numerator. So susceptance of capacitance is given by J omega C. Susceptance of inductance is given by minus J by omega L. That is in the case of parallel resonance circuits. Now the total admittance in the circuit. There are three parallel branches are there. In the resistive part, we have 1 by R. In the susceptance of in the inductance branch is minus J by omega L. We got here minus J by omega L, and susceptance of capacitance branch is plus J omega C. So we have to add all the admittance. Total admittance is given by this. So 1 by R is conductance, and this is net susceptance. So that is a total admittance in a parallel RLC circuit consisting of ideal RLC elements. At resonance, circuit behaves as purely conductive. It means in a series resonance circuit behaves as purely resistive. In parallel resonance, the circuit behaves as purely conductance. So this imaginary part you have to make as 0. So if you make this imaginary part is equal to 0, that is omega C minus omega L. This imaginary part, susceptance part, you have to make it 0. So omega C minus 1 by omega L is equal to 0, and you have to replace that omega is equal to 2 pi f now. Instead of 2 pi f, it is 2 pi f r, or omega r, which is the resonance frequency. So replace omega by omega r. Omega r c minus omega r l is equal to 0. So omega r l is equal to omega 1 minus omega r l, and you bring this omega r left side. See, omega r l square is equal to 1 by LC. So this is 1 by LC value is 1 by LC value is omega r square, and omega r is equal to 1 over root of LC. This is radians per second. Okay, angular frequency r. Omega r is 2 pi fr. Omega r is 2 pi into fr. So if I want to find fr, you have to divide by 2 pi. So fr is given by 1 over 2 pi root of LC hertz. So this is the frequency of parallel resonance circuit. And it is same resonance frequency is same as series resonance circuits. In series resonance also we got resonance frequency as 1 over 2 pi root of LC. In case with this omega r, Okay, it is 1 by root of LC. So next is uh, this is the voltage versus frequency in case of parallel resonance circuit. In case of parallel resonance circuit, voltage is maximum. In series resonance, current is maximum. In case of parallel resonance, voltage become maximum. Its value is equal to V max is given by I into R, and at F1 and F2, lower and upper cutoff frequency, the voltage value becomes Vm by root. In series resonance, current is maximum at F1 and F2. Here you are going to get Im by root 2. In parallel resonance, Vm is maximum at resonance frequency, and at F1 and F2, we get Vm by root. So F1 and F2 are also called as half power frequencies. So you can see that on the either side of omega r means resonance frequency, there are two frequency at which voltage is same. At these 2 points, voltage value is Vm by root 2, and maximum is available at omega r, and that is maximum power given by Vm square by r. So P is equal to V into I. I we can write as V by R. It is V square by R. Vm square by R. And at F1 and F2, okay, voltage value is 1 by root 2 times of maximum. So you can write, you'll get Vm by root 2 whole square by R. So Vm square by R, it is nothing but Vm square by R is nothing but maximum power divided by 2. So it is nothing but P max by, it is nothing but, you're going to get this portion Vm square by R is P max. This is 2. So this is called as half power frequencies. So now we have to derive expression for half power frequencies F1 and F. For this one, you have to find what is the expression for F1 and F2. So at any frequency omega, the total admittance is given for a parallel RC circuit is given by this y is equal to 1 by r j omega c minus omega l. So this is susceptance, net susceptance of parallel RLC circuit, and admittance is given by, the magnitude is given by root of 1 by r square plus omega c minus 1 by omega l whole square, and at omega and omega 2, right, in series resonance circuit, we have root 2 times r. We have root 2 times r, but here in parallel resonance, you can see in parallel resonance at omega and omega 2, z is equal to r by root. In case of series resonance, it is root 2 times r. Here it is r by root. Z is r by root 2. Okay, z is r by root 2. So y is root 2 by r. Z is, because y is 1 by z. Y is 1 by z. So z is actually r by root 2. So r by root 2 becomes to numerator. So at omega and omega 2, y value is root 2 by r. Root 2 by r is equal to this much. And you have to square both sides. You have to square both sides. Root 2 whole square is 2 r square, and root 2 will get cancelled here. So 1 by r 2 by r square, 1 by r square, omega c 1 by omega l whole square, and 2 by r square. If you bring this one to left side, so you left with 1 by r square common. 2 minus 1 is 1 only. So 1 by r square. Okay, 1 by r square you will get, and omega c minus 1 by omega l whole square you will get. Okay, and after that, if you take square root, you will get square root. Root of square is r square. Actually, one more step if you want, you can write here 1 by r square is omega c minus omega l whole square. And now take, after taking the root, we will get 1 by r is equal to omega c minus 1 by omega l. Okay, so now there are two frequency at omega is equal to omega 1. The susceptance of inductance is greater than susceptance of capacitance. So you have to write at omega is equal to omega 1 L. Here you have to write omega 1 L minus omega. This is actually If you take a root, we'll get plus or minus here. You're going to get plus or minus. So one time you have to consider this is greater, another time you have to consider this one is greater. Okay. So omega 1 L minus omega 1 C is equal to 1 by R. And take LCM, omega 1 LC 1 minus omega 1 square LC is equal to 1 by R. And to simplify this, we will get quadratic equation with A value is RLC, B value is omega 1, C value is minus R. Okay, C value is minus R. So then it's a quadratic equation. You can find roots of a quadratic equation is given by minus B plus or minus square root of B square minus 4AC over 2A. So A value is RLC, B value is L, C value is minus R. So substitute here minus B square root of B square minus 4, A value is this, C value is minus R divided by 2A. And simplifying this, you will get this expression. This is the expression for omega 1 in terms of omega 1 radians per second. Similarly, F1 is equal to 1 over 2 pi of this much. This is for series parallel resonance circuit. Ideal components L and C does not having internal resistance. Similarly, at omega is equal to omega 2. So here we consider this is minus, so this becomes plus. So this one minus this one. So another case we have to consider R is equal to minus. We have to consider omega C is greater than 1 by omega L. So at omega is equal to omega 2, that means our upper cutoff frequency, you have to consider omega 2C minus 1 by omega 2L. So omega is replaced by omega 2 because we are considering second cutoff frequency, upper cutoff frequency. So now we have to consider this plus. Okay, this is plus minus. Now one time you have to consider plus, one time you have to consider minus. So at omega is equal to omega 1, we considered minus. So minus into this, that means this part is greater. If we are subtracting the omega C minus omega L, net answer is minus. That means this part is more. So now we have to consider second omega C part is more. Omega C minus this one is positive only. So here omega 2 C minus 1 by omega 2 L equal to R. Take LCM and calculate omega 2 L, omega 2 square LC minus 1 by R, and again cross multiply omega 2 L, omega 2 square LCR minus R is equal to this much. RLC again here also it is in the form of quadratic equation where A is RLC, B is minus L, C is minus R. So omega 2 is given by minus B plus or minus root of B square minus 4AC by 2A. So here also if you simplify this, you'll get LL get cancelled here 1 by 2 RC root of 1 by this much you are going to get. This is expression for omega and omega 2 for a parallel RLC circuit with ideal components L and C. This is omega 2, this is omega 1. Next, bandwidth is given by difference between omega 2 and omega 1. Okay, here you are going to get omega 1, this is omega 2, this gap, this is bandwidth. So bandwidth is omega 2 minus omega 1. So this is 1 by RC. This is the expression for omega 1 we got. This one you got omega 2. And if you subtract, this will get cancelled. This will get cancelled. And you left with 1 by RC plus 1 by RC is 1 by 2 RC. Half RC plus half RC is equal to, okay, 1 by 2 RC by 1 by 2 RC. 1 by RC common. Half plus half is 1. So 1 by RC you are going to get. So bandwidth is, this is radians per second. In terms of frequency, bandwidth is divided by 2 pi. Okay, 1 by 2 pi RC. This is omega 2 minus omega 1. This is F2 minus F1. This is F2 minus F1 is equal to 1 by 2 pi RC. Omega 2 minus omega 1 is 1 by RC radians per second. This is the expression for omega 1, omega 2 for parallel resonance circuit with ideal elements. And this ideal circuit does not exist. Always we use practical resonance circuit where inductance will have internal resistance, and sometimes in capacitance also will have impedance. There are two parallel practical resonance circuits. That is a very, very important derivation that you can see in the next video.